Okay, now we are moving on to triple integrals. Triple integrals are a nice extension of the double integrals. In triple integrals, I would like you to think of dv, the change, instantaneous or incremental change in volume, as dx, dy, dz as just one particular order. Think of a cube in each of these sides, dx, dy, and dz. And these cubes, when added up, create or form a solid. And here are just a couple of these little cubes to get the idea. Now these will be stacked, and we'll sum over x, we'll sum over y, and then we will also sum over z. Okay, what I'm going to do is take some problems from your textbook, and we're just going to work them out together. In problem number 12, they want us to evaluate the triple integral. So I would like to focus on the setup here to get a general strategy of how to set up these triple integrals. So just real quickly, we'll draw the x, y, and z axes. And let's take a look at how this plane intersects the axis systems. So the x-intercept is going to be, what is that, 2? If I plug 0 for y and z, yep, the x-intercept is 2. The y-intercept is also 2. And the z-intercept is 4. Now, if I try to carefully connect these, you get a sense of the plane. And the solid that we're going to enclose is bounded by the x equals 0 plane, the y equals 0 plane, and the z equals 0 plane, so the coordinate planes. So we have this solid here. Now what I'm going to do is shade the base of this solid, shading the part on the Cartesian plane so that we can talk about the strategy here. Okay, now I'm going to look at that projection onto the Cartesian plane. And that projection, let's see, we said it had a y-intercept of 2 and an x-intercept of 2. So if I connect that, I have this triangular region, and this triangular region that I drew right here, and shading in purple, is the same one we see above. Now the entire shape will happen inside that shaded region. The bottommost portion of the solid is this plane. So let me just write it. The bottom is the plane z equals 0. That's the Cartesian plane, and the solid sits flush to the Cartesian plane. Now the top of this figure is actually the plane, and this plane would be 4 minus 2x minus 2y. Okay, that's going to help us. So what we're going to do is we're going to integrate over the projected region, and if we do that, this is a review. I'm going to choose for a minute to fix the x, and the x is going to be fixed from 0 to 2. And then I'm going to go from y, and y is going to go from 0 to that line, and that line is going to be y equals 2 minus x, this line right here. Okay, so that's the xy projection. Now within that projection, the bottom, or if I go into the computer screen as far as I can, where z is negative, the farthest I can go is z equals 0. And then as I go upward or towards you, depending on which diagram you're looking at here, let's draw a different color. So I'm going to go from the z, and that's going to come up until it actually touches the plane. So the top bound then is going to be the plane. Z equals 4 minus 2x minus 2y. And this is going to be y. They told us that. dz for this portion here. And then we went outward dy dx. Now I also can very easily, for the xy projection, I can fix the y to be 0 to 2. And then the x is going to go from 0 to 2 minus y. And then we have the same interior from 0 to 4 minus 2x minus 2y, y, dz. This time I have to switch dx, dy. And I'll ruin it for you by telling you the answer, and this comes out to be 4/3. Just for a minute though, what could that answer represent? Or what could any triple integral over some region x, y, z, some solid region x, y, z, of f of x, y, z, dv, what could that represent? Well, we're back to the mass problem. Suppose that f of x, y, z is a density, and every point inside this region had a density. Then if I summed up these dots or these cubes and I summed them up over the region, then that would give me the mass of this solid object. You could also then make this connection that if we're doing this over x, y, z, where f of x, y, z is simply 1, then that would give me the volume of the solid. In this illustration, we showed two different ways to set up this integral, but you tell me how many different ways can I set up to find this same answer of 4/3. I've shown two. Well, we have all the arrangements of dz, dy, dx, so there should be a total of 6 different ways to arrange them. So while we're still here, let's consider another arrangement. Let's consider dz, dy. So what that requires is I'm going to take a look at the zy or the yz projection. So if I project that onto this back plane, so to speak, I'm going to highlight that in blue, and then I'm going to draw the projection plane. So I have the positive y, positive z, and then that curve is going to connect 1, 2, 3, 4, or intercept rather, at 4 and 2. There it is. And then if I shade that region, the projected region, then I'll keep it blue so you can see the 2 in action. Okay, so now this time, since I have a YZ projection, I'm going to integrate over the YZ region, and then positive x is going to come towards our face, and negative x is going to go into the computer. Okay, so I'm going to choose, since I have it written like this, I'm going to fix the y, and the y is going to go from 0 to 2. And then the z is going to go from 0 to the equation z equals 4 minus 2y. That's the equation of that line. So that's the projection. Then within the projection, so let's see if I can draw this here. We're starting back at this plane, and then we're coming out towards the positive x until we touch the plane. Boy, it's getting a little tricky to see. I'll try another color. We come out until we touch the plane. We start at that back wall and come out until we touch the plane. So our bottom bound is going to be the equation x equals 0. That's the flat flush against the YZ plane. And then when we come out, we're going to come out to the plane, and then I have to solve this plane for x, and that top bound is going to be 2 minus y minus z over 2. And then we have y dx dz dy. And just for completion, I'll finish up this one here where I just switch the y and the z. All right, so that's going to be from 0 to 4, fixing the z. And then y is going to vary from y equals 0 to 2 minus z over 2. And then, of course, we have the x, which is going to be the same thing. I got a little sloppy here. Y, and then that goes dx, and then that's dy dz. And all of these integrals, which end up equaling 4/3, could represent the mass of this solid, where the density at each point is equal to y. The second problem we're going to look at is problem number 22 from the textbook. The directions ask us to find the volume of this particular solid. Okay, so let's draw this. We know here that this is a paraboloid and it's going to open in the positive x. So let's draw that. This circle here is going to end up capping it off, but there's the paraboloid. I'm not too sad about that drawing. Okay, this comes out in the positive x. And then down here we have the positive y, and going up we have the positive z. So that's a look at that paraboloid. Now this thing is also capped off, as I said, by the plane x equals 16. So there we have that. That's the plane x equals 16. And now for the purposes of what I want to illustrate, I'm going to project this solid onto the YZ plane. If I do project it onto the YZ plane, I don't know if you can see that it's going to be the same circle except projected back onto the YZ plane. So I think it best that we just draw the projection plane separately. So this is Y, this is Z, and then we have this circle. I'm going to shade this in the same blue that I just erased. So all the action occurs inside that shaded region. And the equation of the circle is going to be the same equation as this circle. That's when x is equal to 16, so that's y squared plus z squared equals 16. Y squared plus z squared equals 16. Let's set up the integral. So since I'm projected onto yz, I'm going to integrate over that region yz, and I'll worry about setting that up in just a moment. The important part here is that within that region, I want you to see that we go from low x to large x. So I'm actually starting on the paraboloid, and then I come out until I hit the flat plane x equals 16. So here's the longest journey I travel, boom, but then I stop at x equals 16, and I have a little short journey here. So the low end of this is the paraboloid, and the upper end, or the positive end, is coming towards your eyes. The closest most point to your eyes is the plane x equals 16. That's a very important analysis when setting up these integrals. So our bottom bound is going to be x equals the paraboloid, y squared plus z squared, and then the upper bound closest to you is x equals 16. We are trying to find the volume of this, so the function itself is 1, and then the order of integration is dx for this inner, and we'll have to choose dy dz or dz dy. Okay, so if I decide to fix the y, then we're going to go from y equals negative 4, that's out here, to y equals positive 4. And then the z is going to be a negative radical, so that's negative radical 16 minus y squared to the upper function, which is positive radical 16 minus y squared. Okay, and then we are just going to repeat this here. Y squared plus z squared, that's x equals that, to x equals 16, dx dz dy. At this point, I'm going to recognize that the shaded region in blue is a polar region, in which case I'm going to do a transformation. This time, I'm going to say let y equals r cosine of theta, and we're going to let z equal r sine of theta. We certainly know that the absolute value of the Jacobian is going to be r. So let's see what this looks like then. The dz dy region, that will become the bounds, is going to go from 0 to 2 pi in theta. The r is going to go from 0 to 4. And we'll need our Jacobian, which I'll enter in just a moment. And now let's make sure that these bounds are in terms of this polar transformation. So the lower bound now is going to be r squared, and then the upper bound is going to be 16. Let's put our Jacobian in, and then our order of integration goes dz, dr, d theta. Now, just as a forecast, technically speaking here, the transformation that we make is y equals r cosine of theta, z equals r sine of theta, and x equals x. But when I do the derivative of x with respect to r and the derivative of x with respect to theta, those come out to be 0, in which case the Jacobian, which is a 3 by 3 determinant, still comes out to be this r. But for now, I just want you to think of when you transform the space to a polar region, you can slap the regular Jacobian right in to our integral. I'll just cross this out. That's sort of a preview of what's coming next. So I'm satisfied with problem number 22. I know it wants us to find the volume. Right now, I want to really just focus on the setup, and we've done that setup. I'm not going to run through all the 6 ways every single time we set one up. The goal is to set up a good one, and we have done that here. Let's take a look at the third one, which is number 14 in our textbook. We are again asked to evaluate this integral, but my focus is going to be set it up. So we have 2 cylinders. Notice these 2 cylinders have rulings parallel to the z. So I'm going to write my Cartesian plane like this. I'm going to focus on my projection. And z is going to come out towards you, positive z, and negative z is going to go into the computer. So let's take a look at these 2 cylinders. One of the cylinders, y equals x squared, is this cylinder here. Again, and this has rulings parallel to the z. So this big giant ramp is coming towards you like a skateboard ramp. And then we have the other cylinder, which is x equals y squared. Same deal with rulings parallel to the z. Now flush against the Cartesian plane because we have z equals 0. So I'm going to shade that region here. So it's flat against the Cartesian plane at the quote-unquote bottom, and then as it comes towards you, it's going to have a different top. Now, we're not looking at the 3D shape here, but we're going to just analyze it based on the information that's given. So the bottom of this solid, whatever it looks like, is the plane z equals 0, and then it keeps coming out at you until it touches the top version, which is a plane. This point of intersection is easy to find. That's just going to be 1, 1. And now we are ready to set up the integral. I'm just going to fix the x, which is going to be 0 to 1. And then I'm going to go y. Now y is going to go from x squared to the square root of x. And then at the bottom end, z is equal to 0. And then the upper end, z is equal to x plus y. We have our integrand and our order dz, dy, dx. The fourth one is one where we are originally asked to evaluate the integral. What I am interested in, again, is to just set it up. All right, let's go a little robotic. This is hard to visualize. I'm going to picture for a moment. Now, it's worth maybe pressing pause and trying this on your own, but I'm going to work this through. So we have the y-axis and the z-axis for the yz projection. That means positive x is coming towards us, negative x is going into the computer. I see here that x equals 0, so we're going to be flush against the yz plane. I also see here that we have the cylinder that has rulings parallel to the z. So I'm going to go ahead and graph that. That has a radius of 3. Now notice I'm only going to do the quarter of the circle, and the reason for that is we are told that we're in the first octant, and you can figure out what that means. Positive x, positive y, positive z. I don't know how all the octants are ordered, but we clearly know what the first octant is. So we have this quarter circle, and those, again, is a cylinder with rulings parallel to the z. X equals 0 plane, again, that's flush. The z equals 0 plane, that's supporting the fact that this plane here, which comes out at you. Okay, and then let's just shade in this region here. Not an easy one to visualize. If I think of this as x equals y over 3, that's going to be helpful, that plane there, because then x equals 0 is the flat against the paper plane, and the x equals y over 3 is a plane that is seen as we view this from a bird's eye view before we see plane x equals 0. Let's set this up. Okay, I'm going to fix the y. Y is going to go from 0 to 3. Then I'm going to vary in z. Z is going to go from 0 to the square root z equals 9 minus y squared. Okay, then within that projected region, the lower end x equals 0 to x equals y over 3. We have the integrand, and then the order goes dx, dz, dy. We have a polar region here, so I'm going to let y equal r cosine theta, z equals r sine theta, technically x equals x, and then the Jacobian comes out to be just r. So let's adjust the bounds. 0 to pi over 2. R goes from 0 to 3. And then y is going to go from 0 to, let's adjust the bounds, r cosine of theta is our y over 3. Then z is r sine theta. Now I have the Jacobian. Now I have dx, dr, d theta. I would like to approach the same problem, number 18, in a different manner. Suppose we're projecting this onto the xy plane. So here's the y. All right, now how do I draw this? Well, x is going to come out like this. We have this cylinder, rulings parallel to the x. Okay, so here's the positive x. Looks like that. We have the plane y equals 0, so that's going to put us flush here. And then we have the plane y equals 3x, so that comes out like this. Y equals 3x. The way I like to think of this is if you had a log. Okay, so this sort of looks like a log. And then you have a wedge of the log cut out. And then that wedge of this log that's cut out, so it's round. If I touch here, it's rounded, and it curves around to the other side. And then you cut that in half. That's sort of what I imagine as the shape. And you have no idea what I'm talking about, but that's okay. We do have the plane z equals 0, which is going to cut this in half so that we are flat against the Cartesian plane back here, but then as we come out towards us, it's going to be that rounded end of the cylinder. Let's set this up. Okay, so I'm going to fix the x. X is going to go from 0 to 1. Now, where did I get that from? Well, this equation here is going to be y equals, remember that was a radius of 3, y equals 3. So y equals 3 and y equals 3x intersects at x equals 1. Hence, going from 0 to 1 on x. Now y is going to go from 3x to 3, and then here's where the magic occurs. Z equals 0 is flush against the Cartesian plane, and then we come out towards the cylinder, which is going to be the square root of 9 minus x squared. The order here, well, throw in the integrand, and the order here is dz, dy, dx, and just FYI, that comes out to be 27 over 8, obviously. Now in our fifth example, the equation of any plane is not explicitly given, so we might have to find that. This is a tetrahedron, by the way, and so they give us some points. I'm going to look at the XY projection. The XY projection is going to be intersecting 0, 1, so it's going to look like this and look like this. So we have this triangular region here. Shade this in pink. The integration setup, we're going to go from 0 to 1, and then we're going to go from 0 to x. So far, there's no issue there. And now we are going to go from z equals 0 to z equals, well, I need an equation of a plane. Now, I recognize that there are many ways to do this. I'm going to show you just one way so that we can review something here. Let's go dz, dy, dx. Okay, so if I need the equation of the plane, really the equation of which plane, this blue shaded plane here. Now, to get an equation of a plane, one way to do this is to figure out two vectors on the plane. So I have this pink vector here, and that pink vector I'll just call v, and that vector would be 1, 0, 1. And then another vector, let's see, what's a good color I can pick? Green. So that vector could be here. And vector, we'll call it green or u, that vector could be 1, 1, 0. Now, if I took the cross product of these two vectors, v cross u, well, that would give me negative 1, 1, 1. And then the equation of the plane is negative 1 x plus 1 times y plus 1 times z equals 0, as I used the origin as the point. From here, I see that z is simply x minus y. And there we go. There's our setup. This equals the integral 0 to 1, 0 to x, 0 to x minus y, x, y, z, dz, dy, dx. The sixth example, number 10 from your textbook. I'm going to let you work this one out from start to finish. There's not a whole lot of visualization needed. They tell you that what is fixed, and they tell you what y is, and then they tell you what x is. So you basically just have to set up the triple integral, and then I want you to practice integrating this because we haven't done this at this point. Go from start to finish and see if you can get the answer. Now, this is worked out in the notes for you, but the answer is 3/20 sine of 1. See if you can work that out to get that as your final answer. I'm going to let you work out the final example. I'm just going to give you some previews on this. We are taking this and breaking it down to every combination of dy, dz, and dx. The ones that end with dy, dx, and dx, dy, that's pretty straightforward. That's this one here. Then the one on the xz projection, that's pretty straightforward. Here we have z equals 1 minus x squared. So that's pretty easy to work that one out. The final one that ends with dy, dz, or dz, dy, this one's definitely a lot more tricky because if you're looking at the yz projection, it makes a square, but it's broken down by two different shapes. So you can have, like, let's call this the blue region, and then the red region. So the blue has a bottom and a different top than red. Red has the same bottom but a different top, so you'd have to break that down accordingly. So be prepared to discuss this one in class, but definitely take the time to break this integral down to the 6 combinations of dy, dz, dx.